Hey, howdy everyone. In the last lecture we motivated the need to calculate and quantify and to model spatial continuity. Tried to show an example where we looked at how the flow response in the subsurface would change dramatically with different spatial continuities. So given that, we're now motivated, we now know we need to calculate spatial continuity and use it in modeling. Let's go ahead and talk about how we do that. For this lecture, we will limit ourselves to the use of the variogram. And we will then, of course, we'll talk about how to calculate it, how to model with it. We'll go into estimation and simulation with it. We will also get into other types of spatial continuity measures, those such as used in Boolean modeling or marked point process modeling, or maybe more commonly known as object-based modeling approaches, multiple point statistics simulation, and so forth. But for now, we will keep it to the variogram. So we need to quantify spatial continuity. And so we want a function, a statistic, a measure that can tell us about how things are similar or dissimilar over space. And so there we have the semi-variogram. It is a function of the difference over distance. This axis is the variogram value for a specific lag or distance in space. This is the distance in space. And so this measure is showing you how things become more different. There's more difference as we increase the distance. So we're going to make this calculation over offsets in space, defined as a lag vector h. The lag vector h is bold because it is a vector, it has a direction, and it has a distance. We use u to indicate a location. So u gives us the location in the context of your spatial problem to a tail location. So we have a tail, and then we have the lag vector h that describes the separation from the tail to the head. And we are going to make this calculation of the variogram by scanning through our data set, looking for all data that are offset by that lag vector h. We're looking for all possible pairs of data that are separated based on that lag vector h. That's our distance and direction offset. And so in scanning for all the possible pairs, we'll go ahead and use this equation here, where if you look at it, if you ignore the 2 right now, what you observe is that this is simply going to be the tail values, scanning around. This will be the paired head values. We're scanning around jointly together. We're taking the difference between the 2. We're squaring that difference. And the 1 over n function of h is simply going to be take the average of all of those pairs. N parentheses h is simply going to be the number of pairs available at that specific lag vector h offset from tail to head. So it's simply the average of the square difference of all the values that we find that are separated by that vector. The 1/2 is included, and that's what makes it a semi-variogram. If we did not have the 1/2, it would simply be a variogram. You'll notice in my notes, and commonly within geostatistics literature, there is a degree of laziness about reporting semi-variogram versus variogram. In fact, during most of the lectures from now on, I will assume 1/2 of the average square difference, and I will simply term it as the variogram. That's sufficient, and that's what's used within practice. So that's how we calculate the variogram. Now what's very interesting is that every time you take a lag vector h and you scan around, you've got the tail and the head, and you're pairing them up, you could create an h scatter plot. The h scatter plot would simply be take the value at the tail location on this axis, take the value at the head location on this axis, for which they're paired up and we're differencing them, and just plot them. And if we plot them, it's very interesting because if we have a phenomenon for which the values are constant over a separation from the tail to the head over that h lag separation, we would expect that those dots would fall on the 45-degree line. And so if we calculate the correlation coefficient, we'll find out that this would be a good measure of how things are correlated in space. I'll show shortly that's equivalent to a correlogram and can be related directly to covariance, which can be related directly to the variogram. So it is informative and useful, but it's also nice to look at an h-scatter plot and to think about the degree of similarity or correlation over separation distance described by lag vector h. Furthermore about the variogram, once again the variogram equation is shown right here. In words, we would say that it is 1/2 the average square difference of values separated by a lag vector h. Now you may wonder why remove the 1/2, why take 1/2 and multiply it by this? It's done so that this works right here. By taking 1/2 the variogram and calculating the semi-variogram, representing that as gamma, by tucking that 1/2 in there, we ensure that this equation works out, which means the covariance function, which we will define in a little bit, a function or a measure of this degree of similarity versus distance, is going to be equal to the variance of the variable, which we'll call the CIL, subtract the variogram value at that h lag vector. If you look at that, the CIL is a constant. These are both going to vary over the lag distance h. And so this means that the semi-variogram and the covariance function are simply going to be mirror images of each other. We get the covariance by simply taking the constant CIL and subtracting the variogram. We're flipping it upside down. Now, we'll define covariance a little bit more rigorously shortly, but it is very interesting to note, as I mentioned on the previous slide, that if you take the covariance function over h and you standardize by the variance, or if you're working with a variable that has a variance of equal to 1, such as if we've done a Gaussian transform to standard normal, mean of 0, variance of 1, we would be able to get the correlogram. And the correlogram is a measure of similarity over distance for which its value is equal to the h-scatterplot correlation coefficient. We've covered correlation coefficients within the previous discussion about bivariate statistics. We're talking about the Pearson correlation coefficient. Pretty straightforward. And so that's really nice because now we have a function that relates the degree of similarity to a correlation coefficient, which is something that's very natural for us. So we've defined the variogram. We've talked about spatial continuity and so forth. Let's make some observations about the variogram. Let's talk about general things we would see if we looked at a variogram. Now, first of all, what we'll do is we'll give ourselves a very simple data set. It's exhaustive. It's on a mesh. It's very simple. We're able to go through and calculate the variogram at different lag distances, and we'll only concern ourselves with the horizontal, the x direction, just to keep things very simple. So now imagine you go to that data set and you pan through with 2 points, tail and head, tail and head, tail and head, and they're all very close to each other. In fact, they're only 4 cells apart. There's 3 cells in between them. And if you pan through that data set, I hope what you'll observe very quickly is that the degree of dissimilarity will be low. That you will both be tail and head will be high or high-ish. Once again, this phenomenon, this property could be any property indeed. It could be a porosity field. It could be a saturation of a fluid, a contaminant concentration. It could be a density of trees. It doesn't matter. It's a spatial property. And you'll notice that as that lag separation distance increases, you would expect that as you go further apart from tail to head, you have more of a likelihood to have a significant change or transition between the tail to head, going from low to high to low, or high to high. Many different things can happen. So that degree of similarity, or I should say the degree of dissimilarity, goes up, degree of similarity goes down. And so what does that mean? What's observation number one? That in general, as the distance increases, we would expect that the semivariogram value would increase. Okay? So that's our first observation. Is that in general, I'm not saying that that's a rule, but that's something you would observe in general. The other point is that to calculate a variogram, you would use every possible pair. Remember when we talked about statistics and sampling and standard error and all of these concepts, the more samples you have, the better or more reliable your statistics. Its confidence interval will decrease. You have more certainty about your statistic. It's more reliable. It has less randomness. And so we talked about the law of small numbers. We want to have large numbers for more robust statistical representation. So we're going to calculate the variogram over all possible pairs. Now, I have many students who think that when they calculate a variogram on a mesh like this, that you'll anchor the tail and you'll take a close value, the next value, the next value, the next value, next value, and they're done. Or maybe they'll take a lag separation like this and they'll skip ahead to the next bin, the next one, the next one. They won't slide across and get every possible value. So in other words, if you're trying to calculate this case right here for which we have about a lag equals to 10, you would expect that you would anchor the tail here, go ahead here, then you'd move over 1 and do the next one. So you'd go for 10, you would go 1 to data point 11, because there's 10 in the middle. Then you would go from 2 to 12, 3 to 13, and so forth. You would scan across with your 2 points and then scan down, scan across. You would scan over all possible pairs of data with that separation. That way you have the most reliable measure. Now, once you scan through this entire data set, you calculate the square difference between all of those offsets. You summed it all together, divided by number of pairs, which is effectively just averaging or an expectation. You would divide that by 2, all of that hard work, and you get one single point on your variogram plot. So that's a lot of work to get 1 point. That's a good thing computers are doing that, right? And then you would increase the lag separation, repeat. Repeat, repeat, repeat for every possible lag that you want to calculate for. So you're going to scan through and get all possible pairs from your data set for the most reliable statistics. Observation number 3. You need to plot the SIL to know the degree of correlation. And I would say, in order to actually interpret a variogram, you need a SIL. The SIL is equal to the variance, as I mentioned before. So we plot the SIL. That's the first thing you do. Plot the SIL. Now you start calculating the variance. Now I mentioned before the covariance or degree of similarity is going to be equal to the SIL minus the variogram value. So this distance from the SIL down to the variogram value is in fact the degree of similarity. Now, if we're working with a standardized variable, in other words, the variance is equal to 1, that covariance function is actually equal to the correlogram, which means that that value right there is exactly equal to the correlation coefficient of the H scatter plot. And so now you're starting to understand by just looking at this plot, you can see that at this point right here, if you had a data value right here, what would be its correlation? Well, the variogram value at distance of 0 would be equal to 0 because there's no difference. If you compare points with themselves, tail and head are on top of each other, there's going to be no difference whatsoever. So we would expect that the correlation would be the variance minus 0. And so in that case, where we're working with a variance equals to 1, if we have a point down here, the distance right here is equal to 1, the correlation is equal to 1, which is pretty cool. Now what happens if we're at the SIL? At the SIL, there's 0 difference, or 0 distance, I should say, between the variogram value and the SIL value. That would mean that the correlogram is equal to 0, the correlation is equal to 0 at the SIL. That's pretty important information. So when we reach the SIL with our variogram, our experimental variogram values that we're calculating for each lag offset, that's the distance at which we no longer have correlation between tail and head. There's no correlation anymore. So what does that look like? Let's extend that observation number 3. If you were to plot the H scatter plot at the point at which we have variogram value equal to 0.4 and the sill is equal to 1, the correlation coefficient at that distance right there, which is probably around 4 meters or whatever that is right there, about 4 meters, 3 point something, would be equal to 0.6. 0.6 is the distance from the sill down here. So you can interpret that directly. At the sill, at this point right here, the correlation coefficient will be very close to 0. What does that mean? There is no correlation between what's at the tail and what's at the head location. They're uncorrelated with each other. What I like to tell my class and tell people is that if you go to that distance away, so you drilled a well or you gather data right here in space and you go to this distance and it's equal to that distance at which you reach the sill, you no longer know anything. You don't know anything. There's no correlation. You have no information from spatial continuity that can help you with regard to making an estimate or prediction. And if you go above the sill, at that point you have negative correlation. So you go from having no information, now you have negative correlation. Is negative correlation information? Yeah, it's a constraint. It is information to help you with making a prediction at that unknown location. So if you go above the sill, now you have negative correlation, which is also information. Observation number 4. The lag distance at which the variogram reaches the sill is known as the range. As we already mentioned, at the range, you don't have any information. That's the maximum distance you can go to which you can be informed about what's going on, to which you can make an estimate and say, hey, that local data is telling me something that helps me constrain my estimate beyond some global distribution of possible outcomes. And so that is the range. That's the maximum distance you can go away from a sample location and still have some information from that local data that can help you. At the range, once again, the correlation is going to be equal to 0. And I like to draw something like this. If I have a well, I go to the range. Past that distance, I no longer have any information. The range is also an important parameter. When we model variograms, we'll in fact use the range as a parameter that will fit valid variogram models to our experimental variogram results. But we'll talk more about that later. Observation 5. There is sometimes a discontinuity in the variogram at distances less than the minimum data spacing. This is known as the nugget effect. Now, it's pretty common that if you have a nugget effect, you report it as a ratio, a relative nugget effect as a percent, or a ratio that's just simply going to be a fraction. And so if I have a sill equals to 1, the nugget effect is equal to 0.4, I would report 40% relative nugget effect, or I would report it as simply as a 0.4 nugget effect. And that's fine. Either one of them is fine. The nugget effect is a structure that has no correlation at lags greater than epsilon, some infinitesimal distance beyond 0. At 0, the variogram must be equal to 0. If you imagine, once again, at 0, the tail and the head are the same location. You're comparing data, you're comparing the values with themselves. And so that difference must be equal to 0. The variogram must equal 0 by definition. But at that very short distance, it jumps up and expresses a degree of dissimilarity. Where does that come from? The nugget effect term actually comes from gold mining in South Africa. If you imagine a long drill hole and you were assaying it for the grade of gold or the composition as far as the amount of gold in each one of the individual samples along a drill hole, every once in a while you can have with gold deposits naturally forming a large gold nugget, large relative to the size of the samples that we're assaying. And so you're going kind of low gold, grams per ton, and then suddenly you have a big gold nugget. If you were to calculate the variogram going through all possible pairs and suddenly you have a gold nugget, that extreme jump at a very, very short distance, a distance shorter than the minimum data spacing, would result in a level of variability at very short scales that would be reflected as a nugget effect. Now, we've got to be careful of nugget effect because nugget effect could also be measurement error. In fact, if you were to take a just random error and scatter it using Monte Carlo simulation, just scatter it over all of your data everywhere without any spatial structure, that random error would be reflected by a nugget effect. In fact, its proportional relative nugget effect would be based on what amount of variability you put in as random compared to the total amount of variability of the problem. And so you can actually create nugget effect doing that. So what does that mean? It means that many expert modelers around the world will ignore nugget effect within a variogram they calculate because they know it's likely to be measurement error. They feel, or from their experience, they know that the geologic phenomenon, the subsurface phenomenon, the spatial phenomenon they work with does not naturally have nugget effect, and so they don't put it in. The main point is to try to understand the natural system, not to be biased by a measurement error. So, given all of this knowledge, all of these observations, we can start looking at examples. And so we have three different examples of spatial continuity features. You can see the grayscale could be the indication of porosity, grain size, fraction of shale, whatever you want it to be. And we can look at the overall types of spatial patterns from this example, the one at the top, this one right here, and this one right here. They're all the same histograms. They all have, in fact, the same range of correlations. They're all very, very similar. We'll talk about the Gaussian type structure here, but we will term its ranges when we get within, I think, about 95% of the sill. So they actually, in fact, do all have the same ranges. Now, if you look at them, they all have distinctly different degrees of continuity over short, medium, and long scale. Short, medium, and long scale. And if you look at it, you can actually see how each one of these play out and impact the overall type of image. First of all, let's look at the short scale. This structure right here, which we'll talk about later as being the Gaussian type of variogram structure, results in very high degree of short scale continuity. Lots of short scale continuity. Look at the image. Everything over short distances is very continuous. This model here has some nugget effect, but has pretty good short scale continuity. And you can see the salt and pepper, little bit of a discontinuity going on there, short scale, caused by the nugget effect, but overall good continuity. This model has terrible or poor short scale continuity. As a result, when you look at the image, you'll see a lot of disruption at short distances, going from dark to very light gray to white, very fast transitions within colors. This is very poor short scale continuity. Now let's look at the long scale continuity. In general, they have the same range. They're very similar somehow. At these longer scales, the continuity is pretty similar. If you look at the image and you concentrate, focus on it, what you'll notice is that this general area of high, this general area here, this area here, these general large-scale structures are in fact very similar between the images. That's really interesting. So what does it tell us about the variogram? Well, as we become more accustomed to interpreting variograms, we should be thinking about a variogram as breaking apart multiple scales of continuity and being able to recognize that it's like a superposition, that they're all combined as multiple frequencies that are combined together, and we can interpret each one of them separately. And so we have that opportunity. As we move forward with variograms, we'll go back to this idea of interpreting variograms based on short scale, medium scale, and long scale types of continuity structures. The other thing, of course, is this should reinforce the idea that even with the same distribution, you can have dramatically different spatial continuities. That happens all of the time. The other thing, too, is it should make sense that these functions, these representations of the spatial continuity, the variograms, actually do have a pretty big impact in spatial continuity. It's not like it's very subtle. The difference between this, and this are all very different. They're distinctly different phenomena speaking about spatial continuity. So we will get more into interpretation and modeling in the next couple sessions. I hope that this was useful to you. We've now defined the variogram, and we'll carry on with how to practically speaking, how to calculate them in the challenging, sparse, irregularly spaced data types of settings that we often work with, get more into advanced interpretation, and then how do we build valid models that we can use, in fact, for the purpose of estimation and simulation. Thank you very much for your interest. As always, shoot me a question or a suggestion, email, comments, Twitter, Facebook, even in YouTube, whatever you like. My email is very easy to get. I'm a professor here at University of Texas. Thank you.